Hey everybody, hope you're doing well in Florida or wherever you chose to be this morning. We missed many of you, however we didn't really miss you. Okay, in class today we talked about this thing called the chi-squared distribution or the chi-squared goodness of fit test. Okay, we did not get to the chi-squared test of homogeneity, or it's sometimes called the chi-squared test for independence. We'll get to that next week. All right, we talked about it in class today. I think it was the proportions quiz, not exam. The fairness of coins at Mr. Cohen's casino came into question. Perform a chi-squared goodness of fit test to show Mr. Cohen's casinos was cheating or not. All right, so again, at the alpha 0.05 level, so 5%, all right, that's our significance level. All right, these chi-squared tests are in fact hypothesis tests. So, which means we need our null and alternative hypotheses. Now, the null and alternative hypotheses are pretty much always the same for these goodness of fit tests. The data is consistent with the distribution, or the data is not consistent with the distribution. Okay? In class, Savant today brought up, well, then that means it's going to be a two-tailed test. Absolutely not. On the back here, you'll see that every chi-squared test is a one-tailed test. All right? This is what the actual distribution looks like. It is not a normal curve. It is not even a t distribution, which is similar to the normal curve. It looks like this. I believe Jaden in class called it a skewed distribution. Absolutely. Okay. Now, the formula for calculating your chi-squared statistic, we don't need to worry about, but here it is. Just remember, it's the observed minus the expected. Okay. All right, we got assumptions and conditions just like always. Check that the data counts are categorical variables. Okay? That's important because what we do is we use the chi-squared distribution when we are analyzing the distribution of a categorical data. Okay? And notice I'm spelling categorical data with a K. There's a reason for that. While yes, I am bad with the English language and how to behave in public, but that's not in question here right now. The distribution of categorical data, because when we eventually get to it, the degrees of freedom is equal to K minus 1, where K represents the number of categories. Okay, so that's why I spelled categorical with a K. All right, now the other conditions and assumptions, which we're going to ignore for the first few, and then we'll get into it when we hit practice problem number 1. The counts in the cells must be independent of each other. Okay, the counts are available for analysis should be from a random sample from some population. So again, we got our here we've got our categorical data condition. We've got our independence condition, randomness condition. Then the last two kind of work together. We must have enough data for the methods to work. Okay, whatever, but how high? Well, we should expect to see at least 5 individuals in each expected cell. Again, I'm saying expected again because it's the expected value part. So we have our, is the sample big enough? Okay, those two conditions are similar to the whole, number of successes, number of failures greater than 10 when we were dealing with proportions. All right, example number 1. So for those people on that quiz who had Form A, we saw that the coin that was in Cohen's casino had 220 heads, and which means 180 tails. Now, if we are flipping the coin 400 times, we should expect our expected value, again, 0.5 times 400. That means we would have 200 heads and 200 tails. Okay, so here is what we did. Okay, I plugged my data into L1 and L2. Observed, expected. Then we go and we're going to go do our chi-squared test. So stat, tests, chi-squared goodness of fit. GOF. There's 2 chi-squared tests. C and D. The C is the one that we're going to use for matrices when we have bigger and badder stuff. Here, the GOF, goodness of fit test. All right, now, where is it getting your information? The observed comes from L1, the expected comes from L2, and my degrees of freedom is 1. Again, we have 2 categories here, heads or tails. -1, and we get 1. Now, the only relevant information here is the p-value. Okay? So the p-value is equal to 0.0455. Okay, now, if we are testing this at the 0.05 level, that means, well, you know what that means. We are going to reject our null hypothesis. Okay, now it's close, but we're still going to reject the null hypothesis, which means we have enough evidence to show that the data is not consistent with the distribution. Okay, that is to say that Cohen's Casino is using unfair coins. Okay, for the Form B, again, we basically just did the same idea here twice. Form B of that quiz, heads, there were 262 heads, which meant 338 tails. Total 600. So again, half of those we should have expected to be heads, and the other half tails. So again, I already have my data in here in L3 and L4. Observed, expected. So stat, tests, GOF. Degrees of freedom are 1. Again, K minus 1. And now here we get a p-value of 0.0019. Okay, and again, same result, same rejection. So this kind of worked for both. All right, now the second example deals with track runners. All right, many track runners believe that they have a better chance of winning if they start on the inside lane. For the data below, the inside lane is lane 1, and the next lane is lane 2, etc., and lane 6 is the one all the way on the outside. Okay, so here you see I left you a couple of extra boxes. Now, the idea with running on a track is that all lanes are supposed to be equal. So here, the number of observed wins is consistent with the distribution. Okay, that is our null hypothesis. So the alternative is that it's not consistent. Now, how many total do we have here? Add them up. All right, you get 240. Which means our expected here, the expected amount of wins from each lane should be 40, 40, 40, 40, 40, and 40. Okay, now we could check the conditions, which we should, but I didn't. But nonetheless, we have our, let's see, categorical data. Yes, even though lanes 1, 2, 3, 4, and 5, 6 are numbers, they are labels. So we have categorical data. Check. Okay. We can assume that this is a random sample. Check. Whatever happens in one race has no effect or no relationship with any other race. They are independent of each other. Okay? And all of our expected amount of wins are big enough. So our set is big enough. Okay, so we're now ready to proceed with the chi-squared goodness to fitness test. All right? So now our goal is to find the chi-squared value, the test statistic. Okay? And by that I mean we are going to allow the calculator to do the work for us. That's fine. There's no shame in that. So I am plugging in the values here. Okay, and now again, stat, test, chi-squared goodness of fitness test. I am now back to L1, L2. Now there were 6 lanes, -1 degrees of freedom are in fact 5. So my p-value is 0.24. Okay, now the chi-squared statistic is 6.75. Now here's the thing. The smaller the chi-squared statistic, the better. The bigger it is, the further out in the distribution you are. So our p-value is equal to 0.24. What does that mean? Well, that means we're going to fail to reject the null hypothesis. Again, I didn't give you an alpha value, but this p-value is bigger than any other alpha value that we would use. So since, I can't spell, there we go, since the p-value 0.24 is greater than the alpha value 0.05 or any one that we would actually use, we fail to reject the null hypothesis. Now, does that mean that each lane is okay? Well, these numbers show that it's okay. Again, we don't accept anything, we just fail to reject. So the number of observed winds is consistent with the distribution. All right, so the data looks fine. All right, we had one more problem that we actually did in class here. This one was slightly different. Okay, a random sample of car crashes are selected and categorized by age. The results are listed below. Well, the distribution of ages of all drivers is 18% for the youngins, 39% for the middle group, 31% for the older group, and 12% for the senior citizens. Okay? Test the distribution at the 0.05 level here. Now you have to actually do a little bit more work. Well, how many drivers do we have here total? 160. Now, the distribution of drivers is not the same for all of them. Okay? The distribution of drivers has different percentages, which means our expectation is going to be that they are all different. So 18% of 160 is 28.8. Okay? 39% of that 160 is 62.4. Okay, 49.6, and we've got 19.2. And again, if you add all those up, you should get 160. So again, the idea is the same here. So when I plug in my data, okay, I have my data in, and again, same idea. Now, degrees of freedom are 3, again, 4 categories, 3. Notice my p-value's got scientific notation, so it's pretty much nothing. So I didn't write any hypotheses yet, but I got them here. The distribution of drivers observed is good, and then the alternative would be that it's not good. So since our p-value is so small here, we're going to reject the null hypothesis. So that means we're saying the distribution here of drivers observed is good, which means it's actually not. The distribution of these accidents, these car crashes, is not consistent with the amount of drivers in those age ranges. Next week, we'll do some more. Enjoy your trip. Peace out.